Okay, so in this particular PowerPoint presentation, I'm going to walk you through all of the basic probability principles and rules and some basic relationships. And so I'm just going to start off with this first slide. And it's a little bit of review, a little bit of overlap from the other PowerPoint slide in Chapter 5. And this one just again talks about, probabilities go from a range of 0 all the way up to 1, where they say 0 is the probability that an event is not going to happen. Whereas, of course, if it's going to be 1, it's almost certainly going to happen. Now, in the next couple of slides, we're going to talk real quickly about, okay, before you can actually assign these probabilities, you really need to know how many outcomes you have at first. And so basically, once you know your outcomes, then it's at that point that you're going to assign a probability to that outcome. And again, just some basic definitions. If you ever read anything about what they call an experiment, that's basically any process that generates what they call a well-defined outcome. So, for example, you could say, if I were to toss a coin, obviously, we all know there's two outcomes. Those are defined as basically you're going to get either a heads or a tails. And so you could look at, for example, tossing a coin could be defined as an experiment. Now, the next thing is, it says the sample space for an experiment is the set of all experimental outcomes. I'm just going to draw like a rectangle, and let's say, for example, you tossed a coin 3 times. Okay, so you have one toss, 2 tosses, 3 tosses. Just so you know, let this rectangle represent your sample space. That's going to contain all of your outcomes. Okay, and then just another term, experimental outcome is also called a sample point. And then eventually you'll hear me talk about sample points are also called random variables. So eventually we'll just use the concept of a random variable to describe the experimental outcome. Now, one of the first rules in determining how many outcomes you have is called the multi-step counting rule. And you can read through all this, but the basic idea is that if you're doing some sort of sequence of so many steps and you have an outcome for each step, the way you would get the total number of outcomes is basically just to multiply. So again, I'll just kind of go back to the tossing coin example. So let's say you tossed a coin 3 times. So on the first toss, there's 2 outcomes. On the second toss, again, 2 outcomes. And then on the third toss, there's 2 outcomes. According to the multiple step rule, the way you would determine the total number of outcomes would be to multiply. So you would take, for example, multiply 2 times 2 times 2, and you'd have a total of 8 different outcomes. That's called the multiple step rule. And so basically, once you would do that, then the next step is, once you know your outcomes, the next step would then be to assign a probability based on one of the 3 different types of methods we're going to talk about in a moment. Now, I'm just going to mention these because you're not really going to get into these until you get into the binomial chapter on discrete probabilities. But there's a couple more counting rules for determining outcomes. One of them is called your combination, counting rule for combination. And you just kind of look at the formula. You notice you've got some factorials in here. And basically, it just kind of talks about, it's a calculation to determine how many outcomes you can get when you select so many objects out of a set of population objects. And the idea here is order is not important. So if you think of this in terms of like a lottery type of counting rule, like the Powerball, where you don't have to get in any order, any number in any particular order, you would use the combination rule to determine the total number of outcomes. And the other counting rules for permutations, notice the formula is a little bit different than the combination formula, but the only idea here that's different between this is, I'm going to kind of circle this, order is important. So you have to get objects in a specific type of order. That's referred to as a permutation. Okay, now this is basically pretty much the same thing as in your textbook PowerPoint, except you notice once you know your outcomes, there's basically what they say 3 methods to assign a probability. One is the classical method, 2 is what they call the relative frequency method, and 3 is the subjective method. Now, your textbook refers to this as the empirical type of approach, but if you read the definition of how they set you up, they basically say it's really based on relative frequency. So I like to just call this the relative frequency approach. Okay, now, so I'm going to walk you real quickly through each of these methods and then we'll get to the formulas, but we'll start first with the classical method. So again, think of the classical method as, I'm just going to write this up here, it's equally likely scenario. So the idea here would be the probability of each outcome is basically the same. The formula is defined as 1 over n. So I'm going to write this down here, 1 over n. And in this case, rolling a die, there's 6 sides. Each side has an equally likely chance of occurring. There's 6 outcomes. So the probability of each outcome would simply be 1 divided by 6. That's called the classical method. And again, the relative frequency method is kind of like what we did back in chapter 2. So here we have, it looks like a frequency chart. And so what you would basically do is we're going to let this first column represent the concept of x. That's going to be the number of outcomes. And then we're going to let this column represent, we used to call this a relative frequency, or we're also going to refer to it as the probability as well, and you'll see that in the next slide. And as you can see, you basically, to convert these numbers into, I'm going to make a note up here, the relative frequency, or also called the probability, you basically would just take 4 divided by 40, because that's the total number in your count, and you'd get 0.10. You then take 6 divided by 40, and you'd get 0.15. 18 divided by 40 to get 0.45, and so forth. So basically this is what it is. It's a relative frequency chart, but now we're referring to these relative frequencies as probabilities, and you'll notice that the sum of all your probabilities do need to add up to 1. And just remember, the subjective method, is a combination of experience, intuition. You can use some historical data. To some part of it is to your degree of belief. And so, but that's called the subjective method. It's like trying to predict the next earthquake. You've got tons of data, but nobody exactly knows when the next earthquake is going to happen. And that would be more based on some intuition, some science, some relative history. But subjective method is the third type of method to assign probabilities. Now, we're going to walk you through some of the basic formulas in a moment. So the first one is going to mention some definitions. An event is simply the collection of your sample points or your outcomes. The probability of any event, basically what you do is you add up all your sample points probabilities. The sum of all those is going to be the probability of the event. And that's pretty much how we're going to take it when we look at some of the illustrations and some of the other PowerPoint mixes. I always talk about the probability of an event, and then you have to get the sample points in that particular event. So I'm going to walk you through the complement, the union rule, what we call the intersection, and then mutually exclusive events. So as you can see, this diagram is called a Venn diagram. And let's just say the probability of an event is represented by this circle. And let's say that the probability of that event, let's say, is 0.70. If you were going to get the complement of this event, you'd simply take 1 minus 0.70, and you say the probability of that complement would be 0.30. So remember, everything within this rectangle represents your sample space. And so the concept of a complement is 1 minus that event gives you what's called the complement. Next up is talking about what's called the union of two events, denoted by letters A or B, event A or B. And typically you'll see I like to use this symbol to represent A union B. And here's going to be our rectangular sample space. And to start you off with this one, notice that if you look at these two particular events, there is going to be an overlap, and we'll get to that in the next slide. So I like to refer to this overlap. I'm just going to the intersection here. Notice they refer to this as A, like an arch B. Your textbook is going to say it like this. Your textbook is going to say A and B, but I like to use this. It keeps it, for me, it keeps it consistent with the other formulas I use. But A and B, I use this symbol A intersect B, and the idea here is that these two events share some sample point or points in common. And so it's called the addition law. If we're going to find the union of two events, notice it's the probability of A or B or both occurring. And so here's your formula. You simply take the probability of A plus the probability of B, and you subtract your intersection if there is any. And the reason that you subtract your intersection is basically so that you do not double count any sample points that occur in both events. And here's an example of what they call mutually exclusive events. You'll notice they don't touch. And so by definition, I'm going to write this right here, your intersection would be defined as 0, okay, because that basically is telling you that they don't share any sample points in common, and by definition that is said to be mutually exclusive. And again, this is the same formula as before for your union, your addition law. And notice, obviously, if you don't have an intersection, if you're going to find the union of two events or three events or whatever, all you really have to do is add the events, the probability of the events together to actually get that union. Now, next up is this concept called conditional probability. And you'll notice the way you want to read this, the formula is right down here, and you see this P and then an A, and it looks like a vertical line B. Look at this part of it. Basically, the way you want to read this is it's the conditional probability of A given B. So B is going to be considered or denoted as the given condition. And if you look at the formula, you'll notice that the intersection is in the numerator, and this given condition is in the denominator. Now, later on, we'll get to this concept of multiplication law, but if you were to rearrange this equation, you could take the probability of A given B and multiply that by the probability of B to equal your intersection. We're going to say this is going to be what they call a multiplication law that's going to work for dependent events. In other words, the events are dependent. And so this is going to be a calculation, it's called the multiplication law, that in some cases you may need it to be able to solve for the intersection. And we will actually use this concept when we get into Bayes' theorem. And again, I'm just going to label this at the top. This is number 1. This is the first multiplication law. And note, this is the one that is for dependent events. And all you're doing is, if I go back to that basic equation of the conditional probability formula, again, I'm going to write it out right here. All they did in this equation is they took this denominator and they moved it over to the left side of the equation, and that's how they got the probability of B multiplied by the probability of A given B equals the intersection. And then the second multiplication law, I'm going to say this is number 2. This is if the events are independent. The way you could solve for the intersection is simply by taking the probability of A and multiply that by the probability of B, and that's going to give you your intersection. So this is the other formula that works to solve for your intersection if you know that the events are what they said to be independent. And then finally, we're going to do some Bayes' theorem, and I got some other illustrations on some other PowerPoints I'm showing you. But just note that Bayes' theorem is basically an application of your conditional probability, and it's going to be the multiplication law, okay, for dependent events. So it's that multiplication law, it's that first multiplication law. We're going to plug it into these headings down here. We're going to use what they call the tabular approach. And in the next slide, I'm going to kind of draw this out for you. But just note that the first column, which is called your prior probabilities, sometimes that's also referred to as what they say your margins or your marginal probability. The new information is going to be your condition. And then once you do that, you're going to basically take this margin, multiply by that condition to get what's called the joint probability. And then finally, the posterior probability is going to be a ratio of your individual joints divided by the sum of your joint probabilities. And so finally, just the basic idea here. So again, so you're going to have your prior probability, which I tend to label as AI. Then we're going to have your condition, some sort of conditional probability is going to be in there. I'm going to label this column as B given AI. And then the third column, I'm going to refer to this as your joint probability. In the book, they call this the Bayes theorem application, but I'm going to show you in some of the illustrations how this works. And then the last column, which is called your posterior probability, that eventually is going to be labeled as A given B, okay? But just a couple notes. You're going to label this as your margin, okay? That's the first one. Again, this is your condition, and this is your joint, okay? So if I go back for a quick moment, I said this was based on the multiplication law for dependent events. So if I go back to that concept of conditional probability, I'm just going to use this as my picture here. Just make a note that typically the numerator of this equation is represented as also called the joint or the intersection. And I want you to put as the denominator, that's going to be your margin, or also referred to as your marginal probability, but that's also referred to as the given event, okay? And so eventually when we'll look at some tables when you do some conditional probability calculations, and I do talk about this, but this whole thing on Bayes' theorem is based on this idea. And so it's all about labels. And I would just suggest after you looked at this, you go look at my illustrations on my other PowerPoint mixes. I actually walk you through it. We do some applications. I show you what you need to plug in to each of these columns.